Start recording here. Okay, so what we're doing is something called differential equations, and really what we're doing are derivative equations. So it seems kind of going backwards, but we're kind of using derivatives and then integrating. So we're going to take a look at what we look at first, are what we call slope fields. Now, slope fields are like a field, like a flower field, right? A flower field of slopes. So if you look here, we have a bunch of little dots here, and each of those dots represents a xy point, an xy point on my slope field. So it's a fancy way of saying that, look at these points here, and each of these points will have a slope. It turns out that there are infinite many possibilities. But for simplification, what we do is we only pick a couple. So we only pick a couple. And in this case, I actually gave you, like, this is 5 by 5. So this is like 25 different points. It seems like it's going to be a lot of points, but all we're doing is plugging in, saying this. dy or dx, that's another way of saying slope. A change in y, meaning rise. A change in x, meaning run. Rise over run. These are just different ways of writing slopes. And at every point, there is a different x and a different y value. So for example, if I pick a point here, that is 1, 1. Well, if I plug in 1, 1 to that equation, this equation only requires x. So if I plug in x is 1, 1 squared is 1. So we draw a line representing that slope. And what does the slope of 1 over 1 looks like? It looks like up 1 over 1. And that is my slope line. If I pick a different point, let's pick a point over here. This is point 2, 1. Well, the slope over here is just x squared. So we just take only the 2, because that's the x value, and we graph the slope. So the dy over dx here is really just 2 squared. Well, 2 squared is 4. The slope has to be drawn 4. Rise 4 over 1. So I draw 1, 2, 3, 4, go over 1, and that's a pretty steep slope. So I'm going to show you guys some examples as I just search through Google what slope fields are. But we're going to do this repeatedly. So if you do this on a computer, you can draw 100 of them in a second. But drawing by hand, it takes a little bit. So on the AP exam, they might give you like 9 points, 6 points, no more than like 12 points. And the idea is, can you show them what a slope field looks like given an equation for the slope? This is the equation for the slope. Let's pick a different point. I pick a point over here on my left. That's going to be -2, 1. So if I just plug in the x value, so it's dy over dx is equal to -2 squared. That's also a positive 4. Oops, I picked the wrong point. I meant this one over here. I meant this one right here. So the rise over run would be rise of 4, 1, 2, 3, 4 over 1. And that's pretty steep. So you would actually go about, for this whole graph, graphing different points of slope, almost like different points of interest. I'm going to jump down to the answers real quick. Oops. If you look here, this is the graph we end up with. Every point gets its own little mini line, and this mini line is just a graph of its slope at that point. We mentioned before that this slope was going to be dy over dx was 4, so it should be pretty darn sharp. Over here at -2 and -2 right here, we did the same thing. We said, hey, the slope here, -2 squared, was also 4. So this slope, dy over dx, is also going to be pretty darn sharp. At this point here, we said the slope was 1, so it's rise over run. And you would do this repeatedly for all these 25 points. If you look at right in the middle, let me zoom in here. Do you guys see the red? That's a mini slope, because if x was, in this case, 0, and I plug in 0 into this equation, we would end up with a slope of 0. So we actually draw a little horizontal line. Let me draw it red. And we just say, hey, the slope is flat. Now, a couple of points where slope might not exist. If you look at number 2 here, I want you to look at x is 0. If x is 0 and I plug in 0 into the slope field, the slope equation, we would be dividing 1 over 0. Now, does that exist? Nope, the slope does not exist. So if you look here, they just put a dot. You don't draw a vertical line. Essentially, that's what it is, but we don't draw it. Now, look at all the x values here. If x is 0, 0, x is 0, 1, x is 2, 0, 2. All these x values are 0, so they all have the same slope. As you can tell, it's just a dot. So it's not represented by anything because there is no number, there is no slope there. Now, why are slopes useful? It's because when we were working with integration and we went backwards, essentially we were given in many cases the slope. Now, if I give you the slope, what is the original equation? Now, if I go ahead and give you guys, let me get rid of this. Say dy over dx is equal to x. Very similar to what we just saw. This is just a slope. If I ask you, find, well, let me define this a different way. Hey, f prime of x, which is the derivative, another way of saying x, for us, that's our slope. If I say, find regular f, go back and take the integral. Take the integral of x dx. Okay, going backwards. This will give us x squared over 2 plus c. Now, why do we write plus c? Well, do we know what that value could have been? If I wrote x squared over 2 plus 3, or x squared over 2 plus 6, or x squared over 2 plus 100, if I take the derivative of either of these equations, don't we still get the same sloping answer? And the reason why is because these equations, if you remember, just looking at a simple idea of parabolas. If I gave you a graph of f of x, let's say this x squared plus c, isn't that just a parabola? And depending on the c value, it changes where my placement. C could be -1. C could be negative 3. Oops, -3. And C can move up and down depending on that constant value. But when I take the derivative, this all goes away, leaving me just a 2x. And the change is the same in all these graphs. The slope is the same regardless of where I place that graph. So going backwards, this C value changes depending on where I want to place that graph. Now, why are slope fields kind of interesting? Let's go ahead and just search random Google coronavirus. We're just writing slope fields. Okay. I'm gonna go ahead and search. I'm gonna go ahead and look at images, and you will see a smorgasbord of examples of what slope fields are. Now, why are slope fields kind of cool? I think of slope fields almost like currents in a river. Not every part of the river flows the same way. If you guys ever seen people go white water, like rapid, like rafting, like depending on where you fall in the water, depends on where you can get pushed. I once watched when I was a kid the movie It, and if you remember, the little boy puts his little paper boat onto the water runoff and kind of washes away. I think of that for some reason. Now, why did I say that? It's because let's use this example here. This is our slope field. What happens is if I put a dot, you can pick a dot anywhere you want. I'm going to pick just a random point. I'm going to pick a point. Let me go ahead and screenshot this so I can write on this. What if I pick a point right here? Well, what does the slope tell me to do? The slope says, hey, go down this way. Well, then the next slope picks me up, and the next slope picks me up, and the next slope picks me up. It's almost, I'm caught in this river, caught in this pattern, and that is my graph. The slope field tells you where your next point is. It kind of pushes you into the next point. But what if I pick a different point? What if I pick a point out here? What does this slope field push me? It pushes me in this initial equation. What if I put my point maybe a little right here? This says, hey, go straight. I want you guys to look at this real quick. I'm gonna zoom in. Doesn't this point here kind of just say go straight? Fine, go straight. Oh, I'm caught in the next current. That current pushes me down. Oh, this next current pushes me down. This is gonna be vertical here. It's gonna be pushing me in this circle. So essentially, all these slopes are possible. So once you put down a point, that kind of gives us the graph we're headed toward. Let's go ahead and look at another example. This is always a good one. So if you look at their example, I'm gonna go ahead and, you know what, not use that one. Let's use this one right here. This one's not moving. Oops. This is moving. Okay. Let's screenshot this. So to take this example, depending on where I put my first initial point, it tells me which way my graph is gonna go. So let's drop a point over here. So if you look at my point, the slope is telling me go up, go up, go up, go up, go up. If I go the other way, it gets caught up and we're going this way. What if I pick a point over here? It kind of tells me what my graph is going to look like. But if I pick a point down here, this graph is totally different. So given a set of slopes, a set of changes, we don't know what my original graph is till you pick a point. Now, we've actually done this in Algebra 1. In Algebra 1, we see something lame. You guys remember in Algebra 1, if I told you y is equal to mx plus b, and I gave you the slope, m is equal to 2 over 3. Can you guys think of a slope of 2 over 3? Isn't that some graph that just goes rise 2 over 3? Oops. 2 over 3. Now, where does this line land? Is it up here? Is it down here? Not until I tell you x is 2. Let's see, x is 2 comma, sorry, x is 3, 3, 4. Yeah, 3, 4. So if I pick 1, 2, 3, 1, 2, 3, 4, something right there, that is the line we're going to pick. We can rewrite the equation now as y is 4, x is 3, the slope is 2/3. 4 is equal to 2 over 3, x is 3. What's my b value? And what happens is we can start off with the slope, but you can't tell me what the original equation of the line is till I give you a point. Once you lay down a point, we can then plug it in and find what the original graph equation is. So if I plug in as 4 equals to 2 plus b minus 2, b is 2. My original equation, y is equal to 2 over 3x plus 2. So we've done this before. That graph kind of looks like, here's my y-intercept is 2. The slope is rise 2 over 3. Hey, that's my line. But if I pick a different point, if I pick the point up here, this equation will be totally different. If I pick a point down here, this equation will be totally different, though we still have the same slope. And what happens with slope fields, they give you all the possibilities. These are all the possibilities about what the slope could be. But what is the original graph? We don't know till we pick a particular solution. And that's the verbiage. We pick a particular solution. So this is what we're going to do. We're going to come up with working on our slope fields first. Let's see how easy this could be. And then we're going to go and start creating particular solutions, particular y equations, regular function equations that represent the same slope. Okay, let's look at our number 2. I want you guys to go ahead and see if you guys can tell me what the slope would be at 1, 1, 2, negative 1, negative 2, comma 1, and let's do negative 1, comma 2. Go ahead and quickly tell me what those slopes would be. So what happens is we're going to plug them into this equation here. Does this equation require x and y, or just an x or just a y? Okay. So I'm looking at the slope equation. I only require one variable, x. Okay, so at this point here, 1, 1, what do I plug in? If x is 1, this is negative 1 over 1, which is negative 1, or negative 1 over 1. So I graph this line here. You don't have to make it so long, make it shorter. Just a little brief, negative 1. You guys have seen me draw the rise over run. If you look on this side here, see I do a little tick marks, and that's really what you can do. Just do tick marks. Rise over run. In this case, I rise on negative 1. Sorry, I rise on negative 1, and I run a 1. Okay, let's take a look at this next point, 2 comma negative 1. At 2 comma negative 1, we just plug in x is 2, negative 1 over 2, which is negative 1/2. So rise is negative 1, rise is negative 1, and run is 2. So this line is not as slopey as the other one, slightly less slopey. Okay, oops, don't draw the arrows. Over here at negative 1 comma 2, the x is negative 1, so it's 1 over, sorry, negative 1 over negative 1, which is a positive 1. So we just do a rise of 1 and a run of 1. Again, you would do this for all 25 points. I'm just picking up a couple of particular points. If I look here at my last one, negative 2, 1, this would be negative 1 over negative 2, which is a positive 2, sorry, positive 1 over 2. So the rise is rise 1 and run 2. And then that kind of gives me an idea. This is a little flatter. I'm going to pause here. Okay, so let's check our answers. Looking down here, we said our slopes, a couple of these, if you guys looked at your work, this was going to be, I think, negative 1/2, which is a little flatter. See, it's a little flatter than negative 1 over 1, a little flatter. Negative 1 over 2. Okay, we had another point, I think this was right here. This was a negative 1 over negative 1, which is a positive 1. Hey, that's 1 over 1. That looks terrible. 1 over 1. We looked at a point, I think, over here. This was negative 2 comma 1. So that gave us a positive 1/2. So that's flatter, positive 1, run 2. And you would do the same thing for all these points. Now, one thing I want to make sure you guys realize that I want you guys to look at these in vertical values, in columns. If the variable is only x, hey, isn't x the same here for all the values? Isn't x the same here for all the values? Isn't x the same here for all the values? So if you look at the answers right here, all the slopes are actually the same vertically. Because if x is 2 here, that means our slope is -1/2. These are all -1/2. If x is +1, so -1/1, that's all -1. So one thing we can notice that we can actually fill out a lot of these if it's only one variable, and we can find patterns. On the AP exam, when it came to multiple choice questions before, you're supposed to look for some hints. You don't want to just do every point in the world. You want to look for some hints. Like, what would the slope be at 0? Does the slope even exist? Look, that's 0, 0, 0, 0, 0. That's all x is 0. And if we divide by 0, none of the values exist. So you could fill these out pretty quickly. And on AP response questions, that's what they do. They often gives you a couple of values that are going to be the same answer. So you're not really doing all 12. You're really doing maybe like 5. If you notice, this is -1. So negative is a +1, +1, +1, +1. I don't care about the y values. The slope has nothing to do with the y, only the x. So there's a couple of hints that we can take away that makes graphing these a little faster. Okay. Let's just jump to another one here. This one says y is -1. So I don't care about x's. All I care about are the y's. All I care about are the y's. Whoops. And the y's are different, not the x's. All the x values are exactly the same. See, all the x values, because I don't care about the x. I care about the y's. So y here is 1, right? That's so when you plug in 1 here, it's going to be -1. These are all -1. The y value is 0 here. So -0 is still just 0. That's why they're all flat. The slope here is what? Y is -1. So it's -1. That's a +1. That's why they're all positive. Okay. So if you need a further explanation of slope fields, you can ask me, or you can always look at the AP example. Then hopefully they're going to spend like 40 minutes on it, which is kind of wasting time. Okay. Now, what happens is this is not the regular graph. Remember, these are just the slopes. So what would the regular graph look like? Now, don't freak out. Here's the cool part. Given this example here, let's say my slope is x, and we talked about this before. So if I take the integral, isn't the integral here x² / 2, pretty much, plus c, which is a shape of a parabola? I just don't know where this graph starts. Without a particular solution, without one x and y point, I don't know where this starts. But here's the cool part. If I give you a point, let's say the point is 1, 1. 1, 1. That's my point. Well, what would the real graph look like? Well, look at the slope field. The slope field is telling me connect over here. That makes it go higher. This says connect this way. Hey, look, this is kind of flat, flattening out. Once it flattens out, these are all going to be curved up. This is the parabola, that 1, 1. What if I pick a point, -1, -1? Oops. Let's use that in red. That's red, okay? -1, -1, that point here. Hey, the slope is telling me start heading this direction. Oh, flatten out. Oh, once you're flattened out, start curving up. Start curving up. And it gives us a parabola, in this case at -2. And what happens, these slope fields don't tell you what the graph should look like. But if you pick a point, it does trend you into one of these values. Now going back very, very quickly to look at our examples from Google, all these slope fields in essence tell you a direction. Now you can imagine this. You guys have heard of a wind tunnel? Like you drop something and it kind of flows over a car or flows over a surface. If you look at this example here on the right side, I'm going to go ahead and copy and zoom in. If I drop let's say, paper machete, and I drop right here, you can see that the slope field is kind of telling me which line to follow. Remember, these are not the points on the graph. These are all the little slopes. But the slope, it almost is like it's a direction. It's pushing me in that direction. If I drop a point, let's say down here, you can see that it's kind of pushing me in this direction. If I drop a leaf over here, you can see this little line is kind of pushing me in this direction. You can say, Mr. Chico, how do I know it's that direction? How do I know it's that particular solution? You know what? When we're graphing from a given slope field, it really is just a guess. Okay? Now, the cool thing is that anything in physics, anything that's modeling in the real world, people will draw something like that to talk about angles, the way the wind flows over a wing. The rocket ships that they send up to space these days all have this type of flowchart. If you want to go into aerospace engineering, this is a big deal. And all these examples here are just directions. You guys can see here. That if I pick a point, any point you want, it kind of tells you, hey, you're gonna hop into this lane here. If I pick a point over here, it's gonna kind of pick that lane. So all the slopes, which though they're just changes, if I bind them together, it leads me to that next value. And that gives me the next change, which leads me to that next value, which eventually gives me the graph of the original equation at that particular solution. Okay. You can see an example here. They just drew a bunch of different lines depending on where you would put a point. Okay. So how do we come up with that particular solution? How do we go backwards? Well, here are some examples, and they're pretty much just the integral. Now, the problem with this, and then why is it different than just the integral, is because sometimes, if you look here, you do have x and y's, or you might have y's in the problem. And so far, when we've been working with simple integration, it's always been x. Now, I'm going to go ahead and show you guys the process in which we're going to go back to find a general solution, and then we'll find a particular solution. A general solution means I did not give you a point. If you look here, that's a point. That's an x and y point. That's an x and y point. That's an x and y point. If I don't give you a particular point, just like normal, we would write plus c. If I ask you from before, take the integral of x dx, this would be x squared over 2 plus c. That's a general solution. We don't know what our c value is till you give me an x and y point. So let's go ahead and do that. Now, a couple of things I want to make sure you see here. We are going to take an integral slightly different. I'm going to teach you guys this method I use. So I want, looking at number 5, I see dx and dy. So if you guys remember an integral, when we write the integral of something, don't we always have a dx to it? And I'm looking here, I don't have a dx on this side. So what we do is we separate our dy and dx. So our first goal to solve for this differential equation, to find a general solution, is we separate by moving the dx to the other side. The opposite of divide by dx is to multiply by dx. So this will be dy is equal to negative 2x plus 2, parentheses, dx. So dy's are on one side, dx's are on another. If I look at my problem number 6, the same thing happens. If I multiply the dx over, it'll be dy equals to negative 1 over x dx. I don't need a parentheses there, so there's no plus sign. If you look at number 7 and number 8, hey, if I did multiply dy to the right side, why is there a y on the dx side? You're on the wrong side. Look over here. If I multiply the dx to the other side, hey, there's a dy sitting around. You're on the wrong side. I want y's on one side, I want x's on the other. So for number 7, I would not only move the dx to the right, I would also move the y to the left. Opposite of divide is to multiply. This is going to be secant squared y equals to 1 dx. Do I really need to write the dx? No. Let's show that again. What I did was I moved the dx over by multiplying it, and I multiply the secant squared over by multiplying it. And I have one more thing I forgot to write, I'm sorry. The dy. So if you look, I moved all the x's to one side and all the y's to the other. Now, why did we do this? It's because if I want to take the integral, which is my next step, if I take the integral, let's look at number 5. If I take the integral on both sides, what is the integral of 1 dy? Like, what's the integral of 1 dx? Integral of 1 dx is just x. Power rule, if you want to write that. X to the 0 power plus 1 over 0 plus 1 is x to the 1 over 1. You can do power rule on that. So same thing for y. The integral of 1 dy is just y is equal to, hey, look, that's our particular solution. Well, that's our general solution. Y is equal to. On the right side, we have a plus sign, so we can do them separately. So that's going to be negative 2x squared over 2, power rule, n plus 1 over n plus 1, right? 1 plus 1 over 1 plus 1. And then since this is just a 2, it's going to be 2x. So plus 2x. And then since this is a integral, it's not bounded, we're going to write a plus c. So this is our general solution. We don't know where this is graphed because I don't know what c is going to be. So let's go ahead and just double check. Let me simplify this one more time. Y is equal to negative x squared plus 2x plus c. Go ahead and spend like 30 seconds real quick. Take the derivative of this, and do we really get back to this guy over here? The derivative of negative x squared is 2x. The derivative of 2x is just 2. And the derivative of any constant is just 0. So would you guys be okay that this is my general solution? So number 6, I already split it, as you guys saw. Now, do you guys remember what the integral is? So if we follow up with the integral of both sides, after we separate our x's, dx and dy, hey, I've seen the integral of 1 over x. That's negative natural log of x. And then we're going to say a plus c at the end. And that's our y value. Okay, so we know that this is a natural log graph. We just don't know where it's going to be. Let's get a little harder. Number 7, as you guys remember, I separated the y's. I kicked out the y, and I moved dx to both their respective sides. We'll follow up that with the integral. If I take the integral of both sides, what is the integral of secant squared? Which derivative gave me secant squared? Oh, I think that's tangent, right? So this is going to be tangent of y, and then we're going to say equals to x plus c. The integral of secant squared is tangent, and then integral of x is, 1 dx is just x, and then we're at plus c. Now you might be asking, Mr. Go, shouldn't we write plus c on both sides? Yeah, that's a general idea. A lot of people just write plus c on both sides. But if I minus c from c, are these c's necessarily the same c? They're not, right? If you say, I have a friend and you have a friend, we both have friends, but they're not the same friends. So what happens is, I'm going to label this with a little subscript real quick so you guys can see. If I call this C1 and C2, hey, if I minus C1 from C2, well, sorry, C2 minus C1 is just some other C. So what we do is we say, hey, just combine the C's together. That's why we instead just write a plus C. And that C stands for both C's combined. We're not done here. This isn't my particular solution. We are going to go ahead and solve for y. Now, the way we get rid of y, we take the inverse. So tan inverse to both sides. So this is y is equal to tan inverse of x plus c. Please be aware that that plus c is stuck inside the tangent. You can't just kick it out. Unless if you have a rule, which we don't. And you've seen graphs before, like sine of parentheses x plus 3. You can't just say, oh, that's Mr. Code just plus 3, right? That's sine x plus 3. This is totally bad. So we can't just kick it out, so we leave it inside. And that's our answer, our general solution. The next problem here, I see dy and dx is on the same side. Oh no, same side. It's okay. We're going to use basic algebra 1 to separate the function. Let's kick stuff over. Hey, y, get the hell out. That's through multiplication. E 2y dy is equal to, move the dx over to the right through multiplication. It's 2x dx. And now we have to take the integral. But you have to remember the rules for integration. If I integrate both sides, hey, you have a dy, let's do it. This is going to be the integral of e to the y is going to be e to the 2y, and then we're going to divide by 2. Okay, because of chain, in essence, because of chain rule. How to do that so quickly from experience? But if I give you e to the 2y, integral of e to the 2y, we don't have an identity for 2y. So this is where you do u substitution. Du over 2. Sorry, I did that kind of quickly. But if u was 2y, du would become 2 dy, because the derivative of y is dy. Solving for dy, move over the 2. When we rewrite this, this would be the integral of e to the u. dy is now du over 2. Let's move the 2 to the outside. 1 over 2, integral of e to the u du. Hey, the u was 2y. Let's plug it back in. 1/2 e to the 2 y. And if you want, you can double check it using derivatives, and you'll see a chain rule, and that gets rid of the 2. On the right side, the integral of 2x is just 2x squared over 2 equals to 2x squared over 2. And over here at the plus c. Now the rest of the problem is really using algebra 2 to solve for y. Now I'm going to go ahead and pull out the notebook here because it's going to take me a little more space just to work on that. So 1/2 e to the 2y equals to 2x squared over 2 plus c. Let's get rid of 1/2 first, then e, and then the 2. Okay, we have an order. Get rid of 1/2 first, then get rid of e, then get rid of the 2. To get rid of the 1/2, we multiply everyone by 2. E squared y equals to, those 2's went away already, 2x squared plus 2c really, which is really just like a new c, right? Let's call it c1, whatever. And then how to get rid of e? Well, that's a natural log. So natural log both sides. So e 2y, oh, sorry, I did natural log already. So we're left with 2y equals to natural log of 2x squared plus, we'll call that c. Again, well, remember this c is a little different than the other c, we'll call it c1. One last step, get rid of the 2. Y is equal to natural log of 2x squared plus c1 all over 2. And as long as we acknowledge that this is just some c, we can just call that c. So the last part of it is a lot of algebra 2. Now, if you look at my answer here for number 8, same thing. So they gave us the first step followed by solving it. And this is the particular solution. If I went and took the derivative of this ugly little mess here, I would end up with this original equation for the slope, because the slope involves not only x, but also y. Okay, so we're running out of time here. I'm gonna go ahead and finish this last one. Now, what if you end up with a particular solution? The last section here is with particular solutions, meaning I'm going to give you an x and a y. Now, the way they often write it can be various, like a lot of different ways of writing it, but I want you guys to look at this. Is this like y of x, which is the same as f of x? So this is saying f of -1 is equal to 1, which is your x and your y value. So please be aware they might write it a little funny depending on the problem, but it really is an x and a y value, where x is -1, and you get the y answer. The y answer is 1. So for this problem, we're going to go ahead and do what we did before. In this case, move the dx over. dy is equal to -4x minus 2 dx. Hey, now I can, since the x's and y's are on separate sides, we can now just take the integral. Y is equal to -4x squared over 2 minus 2x plus c. Hopefully you guys have been working with the integrals. You guys can do them a little faster, especially if they're power rule. Now, our goal is to find c. I want to simplify this. Y is equal to -2x squared minus 2x plus c. Now, if you look at my answer here, that looks very similar. I just need to find out what c is. Now, how do I find out what c? Just like in Algebra 1, where you guys did y equals to mx plus b. Remember how you guys plugged in the x, the y, and the m, and that gave you the b? Same exact steps here. We're going to plug in our x and y to find that c value. Plug in x is -1, -1. Then plug in the y. Y we said was 1. Plugging all those in, 1 is equal to -2 plus 2 plus c. Hey, the -2 plus 2 cancel out. C is equal to 1. Oh my gosh. And you have to then rewrite it. So we have a particular solution. You gave me a slope, and I said, you know what? This slope has a million possible answers, but you narrowed it and said, you know what? Give me the answer when x is -1 and y is 1. If that's the case, this is the equation that we have. This is the graph that will be presented at that one point. Okay, we're going to jump to number 11, and we have dy over dx equals to x over y squared. And I'm just going to write at x and y point. X is 2 and y is the cube root of 9. That's x and y point. Just so I can see it a little nicer, right, for my brain. It's my x and y. So we see that in the problem, the x's and the y's are on the wrong side. So get the hell back to where you're supposed to be from. Y squared over dy. It's like telling your little brother, get back to your side of the room. Now, hey, I can take the integral of that. Follow up with the integral. That's going to be power rule. So we're going to be left with y cubed over 3 equals to x squared over 2 plus c. And that looks like my answer here, except they have c. I don't have c yet. Now, unless you can simplify, I actually, right now, plug in the values to find c. I find that is the easiest time. Right now, go ahead and plug in the x, plug in the y. X and y seem pretty easy. X we said was 2, and y was the cube root of 9. So if I plug it in, it'll be the cube root of 9 cubed over 3 is equal to 2 squared over 2 plus c. Hey, the cube root and cube get rid of each other, and we're left with 9 over 3 is equal to 4 over 2. That's 3 equals 2 plus c. C has to be 1. Oh my gosh, that's what our c is. Afterwards, we have to solve for our y. So then we would start moving stuff over, get rid of the 3, and then get cube root that. Okay, hopefully you found this helpful.